Hi everyone, I'm Chen-Fatt, a postdoctoral researcher from the AHIAA Taiwan, and I'm great for being here to present one of our main results from the Scuba 2 Ultra Deep Imaging EO survey, the studies project. So the main focus of this talk is on the spatial clustering and the halo mass of the sublimited galaxy. And here I list out all my main collaborators. And I would like to, put some advertisements here. The contents of these talks are mainly from these two papers, and please feel free to read them if you are further interested in. So first of all, I would like to convince you that why we need the far infrared or the sublimited observations. In the 1960s, the IRAS was the first observatory to perform an all-sky survey at the infrared wavelength. And the IRAS showed that the extent of the warm and the cold dust. And you can look at the right panels here. This pair of the image show the Orion nebula in the optical and the infrared wavebands. As you can see here, the infrared observation trace almost totally different regions from the optical ones. This implies that if we only observe our sky at the optical wavelength, we will never fully understand our universe. And also, this figure shows the spectral energy distributions of the extragalactic background in the universe. So you can see the number here, the 23 and 24. So there is a comparable amount of the integrated radiative energy comes from the infrared to sublimited and the UV to optical from the universe. This implies that half of the activities in the star formations and the active nucleus are hidden in dust. This also further implies that if we only observe our sky at the optical wavelength, we will miss roughly half of the story about our universe. So you can look at the red curve here. This red curve shows that the infrared luminous population is insignificant in the low redshift regime, but they play a dominant role in the cosmic star formation at redshift larger than 1.5, which is occupy the same epoch of the peak star formation and AGN activities. So I hope I already convinced you that the far infrared and the sublimited observation are very important. So now we could ask what the infrared luminous objects could be. From the low redshift observations, the infrared luminosity is correlates with the high star formation rates and the galaxy mergers. During the phase of the mergers, the gas will inflow into the galactic center and trigger the star formation, subsequent trigger the dust formations. And the dust particle will absorb the UV lights from the young star and irradiate them in the infrared or sublimited waveband during the starburst phase, in this phase. And the starburst phase is believed to be short-lived, which is about 200 mega years. However, the high redshift sample will not be necessarily in the same case. Our understanding of this population is still incomplete. So therefore, we need to obtain a deep and huge sample size of the infrared or sublimited selected galaxy. So, and now I would like to briefly introduce the sublimited galaxy, SMGs. Typical SMG have the infrared luminosity at the range of the 10 to the 11 to the 10 to the 13 solar luminosity. This figure shows a typical SED of the SMG, and you can see that the SMGs are extremely bright at the sublimited regimes. And you can see that when an SMG with a fixed luminosity is pushed back in the higher redshift, not only the wavelength will become redder as shown in the as the arrow here, but also the flux will become fainter. So you can see that the total effect will shift the entire SED into these directions. So compared to the optical regions and the radio regions, the observed flux in the sublimiter regimes only slightly drops or even slightly increase with the increase in the redshift. So this is so-called the negative K corrections. The negative K correction will lead us easily to detect the SMG at high redshift. And also, if we assume an evolutionary track like this figure show, the SMG reside in the halo mass of around 10 to the 13th solar mass, which is believed to be the progenitors of the massive systems in the local universe. However, is this evolutionary track correct? So let me give me more explanations. So here I show the clustering evolutions of the SMGs from the redshift 0 to redshift 3. And the y-axis of this figure is the clustering length. You can simply think that the larger values of the clustering length indicating that the galaxy reside in larger halo mass. So for instance, if we project the halo mass information in this diagram, the galaxy that reside in a larger halo mass have larger value in the y-axis. And we found that the SMG at the redshift around 2 seems to reside in larger halo mass compared to the population in low redshift. However, is this can we say that this is evolutions? Probably not, because we found that there are two different populations because they seem to have different infrared luminosity. So now I would like to ask, can we obtain more brighter objects at the low redshift bins? And you also can see that even at the same redshift bins, some studies even do not have do not consistent with each other due to the small sample size. So another question is, can we narrow down the error bars? And there's a gap between the redshift intervals of the 0.5 to 1. So can we fill up the gap with more data points? To address these questions, we require a huge sample size of the SMG across the redshift range of the 0.5 to redshift 3. So now I would like to briefly talk about the SCUBA tool from the JCMT. The SCUBA tool is a very powerful instrument that can scan the 450 and 850 microns image simultaneously. The spatial resolution is about 8 and the 15 arcsecond at the 450 and 850 micron respectively. And the 450 micron actually is very sensitive to the water vapor, so it's very hard to detect in our Earth. So now I would like to introduce our project, the STUDIES project. The STUDIES is an ENO JCMT large program that observes under the best weather conditions in the Mauna Kea. The STUDIES aims to construct a confusion limit 450 micron image, which will be the deepest image ever in the far infrared. The Daisyscan mode is used in this survey, which maximizes the exposure time in the center regions, as shown in this figure. Sorry. And the studies will observe into two different fields. One of the two is in the Cosmos field, while the other one is in the UDS field. The total integrations time is in each of them is about 300 hours. And up to that, the studies in Cosmos field is already done. And the noise level is about 0.6 millijansky in the deepest regions. So by combining our first release data and the old SCUBA 2 archive data, we construct an extremely deep 450 micron image in the cosmos field. And then we obtain 164 SMG with the 450 micron flux larger than 4 millijansky from an area of the 300 square arc minutes. And all of these sources have the optical counterparts in the Cosmos 2015 catalog. And caution about this because the sample size from the studies is far insufficient to do the clustering analysis. As I mentioned before, we need like 1,000 sources to do the clustering analysis. So in this step, we use the machine learning to increase our sample size. So first, we adopt our 164 SMG and around 5,000 field galaxies resides within our 450 footprint. And then we label them into 2 different classes. And then we use them to be the training sample. And we develop a machine learning algorithm using their K-bands magnitudes and the 78 colors measurements from the 13 bands photometry. And we verify that the extreme gradient boost, the XG-BOOST model perform the best compared to other algorithms. So after we train, the models, we then take the opticals selected catalogs from the Cosmos 2015 as an input to the trained models. And then note that this catalog contains about 300,000 optical selected galaxies. And the trend model labels about 6,000 SMG candidates and across a very large area. So by using our algorithms, we can know which galaxy is SMG even without the time-consumed sublimiter observations. And also, we dramatically increase the sample size by around 14 times. So the machine learning is a very powerful technique for the data analysis. However, it appears to be a black box to us. Therefore, it's necessary to do some checks. From the number count analysis, the expected finding number of the SMG is around 6,000 in the 1.6 square degree area. And this value actually is consistent with our finding number, the 6,182. Another thing is we employ the stacking analysis in the shallower wide field scuba 2 survey. And the median stack flux of the 450 micron flux is about 5 millijansky, which indicating that our SMG candidates are robust. And some of the area also have the ALMA observations, which have a higher spatial resolutions and a higher sensitivity. The high completeness and the high accuracy of our sample in the ALMA observations further supports the reliability of our machine learning algorithms. Here I show the redshift and stellar mass distributions of our submillimeter candidates and the submillimeter galaxy training sample. The redshift and the stellar mass distributions of the SMG candidates are consistent with the parent training samples, indicating that our SMG candidates are robust. So now I just quickly show some physical properties of our SMG candidates. And in general, the SMG candidates are dustier and younger in the stellar age, larger in the physical size, and more disliked compared to the star-forming and the passive galaxy. And all of these findings enhance our knowledge about the formation of SMGs. So in finals, we apply the 2-point angular autocorrelations technique in our SMG candidates. And by using this figure, the results, we can constrain the dark matter halo mass and the clustering signals. So now we can revisit our aforementioned questions. So by using our algorithm, by using our machine learned SMG candidates, we obtained more brighter populations, even down to the redshift around 0.5. And we also narrowed down the error bars at the redshift around 2 by a factor of at least 2 due to our larger sample size. Our sample also put one more significant data points at the between the redshift interval of the 0.5 to redshift 1. And in conclusion, we found no evidence that the halo mass of the SMGs have evolutions with redshift. The SMG reside in the typical halo mass of the 10 to 13 solar mass, which is consistent with the previous finding. And here I just show the take-home message from my talks, and thank you very much. Thank you.